Great, thank you. Thanks for the invite, and it's a pleasure to talk about our work. So mostly what I'm going to talk about today is graphs as a framework for scientific machine learning, and I'm going to assume people don't really have a background. So I'm going to lead in with a motivation of why graphs at all. Why is that an interesting framework to look at, and especially in terms of applications, what's kind of driving the research that we're doing. And I'm going to take a deep dive into the stuff that we're doing to use graphs as a tool for building data-driven models. And then I'll give a little bit of outlook about what we're trying to do with causality and so on at the end. So a lot of what I'm presenting today is the focus of this new center called COINFLIPS. And the idea of the center is that we're building next generation machine learning architectures. And it's really like, we don't want to take off the shelf convolutional networks, all the stuff that worked in natural language processing or image processing and so on. We want operators that are designed with scientific computing in mind. So that's operator regression frameworks. For this audience, everyone knows spiking neural networks. We're doing a lot with that. But what I'm going to focus on today is graph neural networks. And so there's a number of institutions shown here who are part of that. But the real hope is that we can design these architectures so that they can build surrogates of physical systems or data-driven models that are 1,000 times faster than a traditional finite element type simulation. And on top of that, we want these to consume less power. So we're interested in power efficiency, and that's why we're looking at things like spiking neural networks. And what we'd like to do with these is build digital twins of complex systems. I'll talk a little bit about what I mean by that if you're unfamiliar. But this really, going after something like a digital twin, mandates these kind of improved, like drastic improvements in performance and efficiency in order to support the kind of tasks that we'd like to do. And so I'm sure for this webinar series, people have shown slides like this all the time. There's discussion about microelectronics co-design and thinking about hardware and how do you design hardware with machine learning in mind. The perspective that we look, I'm also interested in this sort of stack, this co-design stack, but we're looking at it from the mathematics side, right? So instead of saying like, yeah, we have a multi-layer perceptron, how do you design hardware that will run well for that? What we're interested in is maybe revisiting a lot of the algorithmic choices that people make and look at alternative architectures that may map better down onto hardware. Okay, so the first question of why we want to look at graphs is we're looking at building digital twins for systems of systems. So a system of systems, maybe the canonical one that we're interested in is the climate system, where you have atmosphere, ocean, land ice, sea ice, earth models, and so on, all coupled together, right? So in some sense, you can view each one of these subsystems as the nodes of a graph with edges describing the exchange of physical fluxes and conservation statements in between the two of them. And when we say we want to make a digital twin, specifically what we have in mind is that you want something that can make a forward simulation. So E3SM and traditional first principles models give you this, right? So you want to make a prediction about the physical system using the digital system, but then you also want a closed feedback loop where you're performing data assimilation of the physical system to update your digital model. And all of this has to happen in real time. So the objective with these kind of things is that you can use this for performing optimal control of these sort of complex systems of interest to DOE. And real time is obviously problem dependent about the actual physics that you care about, but this is something where traditional large scale simulation, like exascale type finite element based things, just aren't fast enough. Like you need something that's a lot more lightweight in order to support these kind of goals. So some of the things that we're interested in, real-time prediction, stable coupling, meaning it will support verification and validation. You can prove that a model that you build in this sort of data-driven machine learning sort of way has the same guarantees as a traditional finite element simulation, data assimilation. Some of the stuff that I'm most interested in and I'll talk about today is physical and causal structure preservation. So physical, that would mean you need something that'll make physically realizable predictions. So stuff has to be conservative. It can't violate, for electromagnetism, there's certain like gauge symmetries that you have to respect and so on. So we want to design architectures which, you know, they have to be very, very fast, and they give these reducer descriptions of a system. But they'll do that without violating these kind of constraints. So these systems are ubiquitous, especially at Sandia across the whole lab. You can apply these tools, and we do, to different systems. We're interested in mechanical assemblies, different material science problems in terms of bridging scales and going from process to structure to property when you're designing novel materials. Fusion power, this kind of structure preservation is extremely important in order to handle magnetohydrodynamics, and there's a lot of like very delicate subtleties there. But the punchline is that graphs naturally describe the exchange of fluxes. And once you have that, you know, you have something mathematically, people call it a Dirichlet-Neumann map, but you have a way of exchanging information between submodels where you can actually prove a lot. And you can prove that it's not just like you cobble these things together and you hope it works. You actually want a stamp of approval that, yes, I can guarantee it will work and it's not going to explode. So specifically in microelectronics, there's this co-design idea that you know, you want to design a system and you have this stack of models from materials to devices up to architectures and algorithms and so on. And so what people traditionally do is they take big production codes, they work on their little piece of the puzzle, they're siloed off, they just like toss their analysis over the fence up the rungs of the ladder and so on. And so basically maybe you can do like a one-way sweep up that ladder for a given design. Maybe you can do 2 or 3 iterations of that where you go back down and start over again at the end of it. But as you go to smaller and smaller devices, physics are getting coupled more strongly, and you can't design these things in isolation, right? You'll have stuff like coupling, you'll have resonances in between components and so on. So really you need something with bidirectional coupling, where you have these models that can actually account for the system scale geometry, right? Or maybe your components, they're parasitics, right? That they can see each other in the geometry of the layout. And so we really need better modeling tools, so that way we're not making restrictive assumptions when we're doing our design. And so for traditional CMOS, you have this kind of pipeline, right? That you might do like huge DFT or MD campaigns to get a material right. You do a component model for a single transistor. For finite elements, you're talking about 1 million elements. At the device or system level, you could have 1 billion transistors in a given device, right? So it's absolutely massive, the scales that you're attempting to bridge. And so for something mature like CMOS, that's fine. People have developed that empirically over decades. But now that you're going to novel materials, like at Sandia, we're interested in gallium nitride materials. We did some work with silicon photonics, rad hard materials, and so on, right? All of these, you can't just like take a decade to come up with new models. You need to rapidly come up with ways to surrogate out these really expensive rungs of the ladder, and that's what this is all about. You know, so hopefully that motivated digital twins and why we want to use graphs to build surrogates to bridge these kind of scales and look at system scale engineering. The other piece that we're interested in graphs is that they naturally expose causal relationships in data sets. So here's an example, if you're not familiar with this before, and everyone's probably heard of correlation versus causation in some way, shape, or form. But the idea is that a joint distribution over 2 random variables is not enough mathematically to infer what causes what, right? So if you have an event A and B, you could write it in terms of conditional probabilities in a way that makes it look like B causes A, or you can make it look like A causes B. And through Bayes' theorem, you can trivially rewrite this. So it looks in either way. And so there's this nice example from Charles Kopp's textbook that I like to share that makes it clear how it's so unintuitive. So if you think about the question of, say you've got a bunch of cities and you have their altitude and their temperature, you might be tempted to say that altitude causes temperature from physics. Like obviously you go up high, it gets cold and so on. But it could easily be described in terms of the second direction, because maybe people who want to have ski resorts do that on top of a mountain, and people who want to have beach resorts do that at a beach, right? So in some sense, like the temperature tells you what altitude someone's going to attempt to found a city at, right? And this is why it gets so messy. But from an engineering perspective, it very quickly gets philosophical and confusing when you're digging through the literature. But in an engineering perspective, it's very clear what we want, right? We want a causal mechanism that we can identify and exploit. So for example, a precursor to failure, you're flipping a transistor a billion times, what happens at the 900 millionth switch that we could identify that tells you it's about to go bad. So what's interesting is there are many different notions of causality. This is just one of them, the Reichenbach's common cause principle, links causality and probability. And the core is that you need something extra beyond just probability and conditional statistics in order to characterize this. And in this case, it's a directed acyclic graph. So the idea is if you have, there are these two assumptions that if X and Y are statistically dependent, then there's a third variable Z, which is causally influencing them both. And if you have a valid causal decomposition, once you condition on Z, then X condition on Z and Y condition on Z are independent with each other. So the idea with this perspective is that once you have a DAG, a directed acyclic graph, right, that plus probability is sufficient. It's kind of the idea behind this whole line of reasoning. And that allows you to decompose, if n is a vector of random variables that you want to establish causal relationships in between, you can decompose their joint distribution in terms of this, the product of the conditional probability of a node conditioned on the parents of that node. And you can see why a DAG is important, because it removes the possibility of circular reasoning, right? You can't have A causes B causes C causes A. That's what's important about a DAG. But the real challenge about DAGs, and why people have struggled with this for a long time, is that they're inherently combinatorial and discrete. So what people will do is they've got a bunch of nodes, they build the space of all DAGs, and then they do statistical tests on each one to ask whether A causes B or B causes A, and so on. But that's combinatorial, and the dimension of that explodes as you go to very high dimensional problems. It very quickly explodes, right? You can't even look at like 10 variables. So the idea is that I'll show is how you can use machine learning in order to discover DAGs without, getting away from this combinatorial setting and without doing this brute force cost. Okay, so hopefully I've motivated this a little bit, right? But that for high consequence engineering applications, you really need these properties in order to make it work. So I'm about to take a deep dive into the math and go into math, applied math, la la land, right? But there's something you really need here, that when people are doing, there's all sorts of stuff that's popular right now, like physics and for machine learning and so on, that try to get these 1000x speed ups, but they don't have these guarantees. So at a place like Sandia, we can't design like a high consequence system without having these sort of guarantees that we've come accustomed to. So hopefully I've made that point. Okay, so before we get into the math, when, and maybe for this crowd, this is maybe more neuroscientists and electrical engineers, but in mechanical engineering, when you design a bridge or something, for example, the way that you're taught this at the undergraduate level is they teach you something that I'd call engineering judgment, which is that, say you want to look at all the forces in a truss system like this, you can do some of the forces is equal to 0 and so on. You get a system of equations, one equation per truss element, and you can solve this thing, and it's huge. But what they teach you to do is you draw a control volume around the whole thing so that you don't even need to worry about all of the details. You can creatively set the problem up so that you get a single equation that just tells you what the force is in a given load. All right, so I call that engineering judgment. That's the kind of thing that's very difficult to get computers to do, right? You can set up a big linear system and solve and let it rip, and that's great, but it's difficult to actually get a computer to think creatively, not that a computer can think, right? And so the same thing sort of happens all over fluid mechanics and so on, where people will strategically draw what's called a control volume, and you'll say, okay, I want the sum of the fluxes in and out of this subdomain to be balanced, but you'll strategically draw that control volume in such a way that you get a simplified but informative analysis, right? So that you can do a lot of stuff with pencil and paper. So what I'm about to show, I'm going to start with the punchline first. What I'm going to show is a framework to discover models where you use AI in order to do that. And so what I've shown here, these are two analytic solutions to potential flow past a sphere. The dashed lines are the true solutions. We're trying to discover a model, which are these solid solutions. And these lines are the streamlines of the flow. They show where the velocity is going. And so when you train, what you can see is that we're asking for control volumes. That's these kind of polygonal-ish looking subdomains in the back, under the constraint that, so we ask for subdomains such that a integral conservation balance holds over each one of those domains exactly. So we don't know what the fluxes are. Like, we're going to discover what the fluxes are, but the point is that it'll tell us this. And so what this is doing is it's taking, cats in classification, you say this part of space is the cats, this part of space is the dogs. You're taking these same kind of classification architectures, but you're using them in order to partition up the space. But once you've got this, now you have as many degrees of freedom as the number of subdomains. It's something like a finite volume method, if that's a meaningful thing to you. And so now you can solve this thing, right? So it's like a 5x5 system that you can get, and it's been trained to match the solutions to this. And this is different from doing, it's different from building a surrogate, right? Because we're actually learning a model. And so this is something that can generalize outside of our training data set. Okay, so that's maybe a distinction. That's, people are trained to just think machine learning means you can't extrapolate, but you can in this kind of setting. So the framework that we use for this is compatible spatial discretizations of PDEs. It's a really elegant theory, but it brings in ideas from algebraic topology, and it connects the geometry of, in this case, these partitions of space together with the physics. And it's a framework where you can actually prove a tremendous amount. And at Sandia, this, Pavel, who was my postdoc advisor when I came here, this is how we're able to simulate things like the Z machine at Sandia, right? With finite element spaces that are designed with this kind of mathematical structure preservation in mind, we would never be able to do traditional forward simulation. And so I'd argue that in machine learning, like we need the same thing. Like, now's the time to develop the same thing. Okay, so first I'm going to present this graph exterior calculus, and the key takeaway is that everything you know from vector calc in undergrad, the same thing holds on a graph. There's a graph gradient, a graph divergence, a graph curl, and so on. And it all works pretty much the exact same way. So the things you need to know is, what's a K-clique? A K-clique is an ordered collection of nodes. A node is a one-clique, an edge is a two-clique, and so on. You can have higher order collections. And there's something called a graph coboundary operator. And all this is, this is something like a graph gradient or graph curl or divergence. It's something that maps a K-clique to a K+1 clique. And so, for example, it's defined in this abstract way, but down here, if you look at the graph gradient, that's just the difference of nodal values, right? You take the difference of values at nodes in order to get something that lives on an edge, right? So that would be one example of these guys. And these, you should think of these as matrices, right? These are just matrices that we have a formula for how to derive them. And so they have some really interesting properties. So they form something called a Hodge Laplacian. If you're familiar with a graph Laplacian, that's one example of a Hodge Laplacian. But these are operators that you can prove a lot about. You can prove that they're elliptic, semi-definite. You can talk about the null spaces of the operator. You get exact formulas for them. You get all these nice things to support analysis. And then you have an exact sequence property. So that's what you know, that like the curl of a gradient is 0 or the divergence of a curl is equal to 0. You get the same thing in this graph setting, which has some really profound consequences down the road. So all of these things build something that's called a de Rham complex. And this just means these are functions defined on nodes. These are on edges and so on for higher order k-cliques. You get operators, you have these co-boundary operators, these derivatives that map from nodes to edges and upward. And then you have their adjoints that take you back down. And this encodes all of this structure, right? This exact sequence structure is encoded in this diagram because if you go 2 hops over on an arrow, right, it's guaranteed to be equal to 0. So that's what makes it a de Rham complex. It's a commuting diagram. So it's an abstract mathematical way of representing this property, this exact sequence property. So the whole idea behind all the work that we're doing is that you can take that graph de Rham complex and you can parameterize it. You can introduce some machine learnable information that will endow the graph calculus with more information, with some approximation properties. You do it to match data, but you do it in such a way that it preserves this commuting diagram, right? So if you have that the graph gradient of the graph curl is equal to 0, now we take one of these learned operators, come down, and then we get the same thing, right? By preserving this commuting diagram, we have trainable operators that preserve the same structure without messing anything up. So if you're familiar, there's a lot of stuff here that I could give a whole talk about. We would just put in a NeurIPS paper about this. But basically, you can view attention mechanisms in graph attention networks. You can view those in these frameworks, that these trainable things that we're learning, a graph attention mechanism would be one example of something that falls in this framework. But now we can analyze it, right? It's not just like graph attention where somebody just made it up. Like it's actually tied to some analysis. You can prove a ton of things, right? You can prove this exact sequence stuff that I talked about. You get something called a Hodge decomposition. For example, like in vector calculus, you might be familiar that a vector field can be decomposed into the gradient of a scalar plus the curl of a vector potential. Those kind of things. You get what's called a Poincare inequality, which lets you prove stuff about whether the Laplacian is invertible, so on and so on. I'm not going to talk about the math. I'm trying not to give like a math talk, just an overview. But the point is that these are the building blocks that we use in finite elements in order to actually prove things. And so this whole framework gives you access to the same building blocks. So instead, I'm just going to show how you would use this. So if you had, for example, a high fidelity PDE solution, and you post-process that onto a Corson graph, right? So in this case, we just took a finite element solver, we pushed it through Metis to get a bunch of subdomains. And now that induces a graph, right? You have a node for every subdomain and an edge in between them. What we can ask for is to train a graph model which will reproduce a high fidelity PD solution. But the point is that we want to do this in a way that preserves conservation structure, right? Like we know conservation holds. We know mass is conserved, for example. And so we can write that as saying, all right, I want to model that the divergence of the fluxes is equal to the sources, right? That's exact. It's exact physics. You don't need any machine learning for that. You don't want to waste data trying to machine learn that. But now we're going to say those fluxes look like something like a graph gradient, which is a diffusive flux, plus a black box deep neural network flux. So this is exactly like a message passing graph neural network, if you're familiar with that, right? But now it's recast in this language of physics, which is going to let us analyze it. And so you can do this, and you can abstract it, and you can look at like different classes of conservation laws, like for Maxwell, you have a conservation of curls instead of divergences, right? So you get different versions of these things. You can always write it as a generalized fluxes, which are a diffusive flux plus a black box neural network flux. And you can show, and I'm just skipping all the math, but the punchline is that you can show that you get a invertible bilinear form. So this is like the diffusion plus a nonlinear perturbation of that. So this is the black box neural network. And now you can exactly enforce physics by doing PDE constraint optimization. So you can say, give me a model that matches the data such that we know that the model has this form. It's a very expressive model, right? It's like a black box nonlinear flux. It can capture all sorts of different kinds of models without actually having to guess what the physics are, do any pencil and paper derivation. But the point is that you can prove that this has a solution, right? That essentially the diffusion stabilizes the nonlinearity. You can prove that this is well posed. You can force this equality constraint. And that's how you get models which are exactly conservative, basically preserves all the structure. So that's fine and great if you have a network for your data, right? So, you know, we do a lot of stuff that's like data-driven circuit models. If you're familiar with what a compact model is, you know, we do that kind of modeling for semiconductors. People do this for thermal circuits. People do this for neural circuits. In fluids, there's something called hydraulic networks. All of these are basically like you take Kirchhoff's laws and you generalize them. And so with a graph, we can fit a model to a graph, given data on the graph. That's kind of the punchline on the left. But a lot of data doesn't come with a graph, right? So how do you discover a graph which actually encodes physics? So say somebody gave you experimental full field data, like a velocity field. In this case, this is a video of the velocity field behind a flying bird. This is typical of what you would actually get from experiments. So how can we build these kind of surrogates from something there? And the idea is that we can work through what's called the finite element exterior calculus, where there are finite element spaces which implicitly define a graph. So if we can discover a finite element space, that will implicitly reveal a graph which encodes the physics of a problem. So in order to understand that, I need to introduce a few things. One thing is called a partition of unity, which is a set of functions which are positive and sum to one. And as an example, you can think about like indicator functions on a mesh, right? That's something from traditional scientific computing. That's an example of a partition of unity. But machine learning, you know, we steal this kind of from classification problems. You can get a different kind of partition of unity by taking the softmax of a black box neural network. And so in this case, like the partitions, they're not disjoint, right? They diffuse into each other, but this is something that's a trainable partition. So we can get a partition of space just by playing with the weights and biases of this neural network without building up a topological, like the nodes, edges, faces, and cells of a mesh and how they're all connected. This is like a differentiable version of the same object. And we'll show that it has the same topology to it that lets us get a ton of physics out. So, you know, you can do things like same way finite elements, you would do piecewise polynomial approximation on a mesh. You can do piecewise polynomial approximation on this partition of unity. And we use this for non-parametric regression. I won't talk about this other than just to say there's some really incredible exploitable structure here, where in traditional machine learning, you might try to do a supervised learning problem. And if you get like 2 digits of accuracy, that's great. For scientific machine learning, that's unacceptable. You need to be able to get arbitrarily whatever accuracy your problem demands. And so that's why in finite elements, you need consistency theory and approximation results and stuff like that. So in this architecture, you can actually get things that, you know, like machine precision, accuracy, and HP convergence, if those are interesting things to you. So I won't talk about that as much here. I'm talking more about the topology of this partitioning of space. So the idea is if we want to talk about conservation, what we need is the idea of the boundary of one of these partitions, right? So if you think about the Gauss divergence theorem, right? Typically, this is how like a finite volume method would work, for example. The divergence of fluxes on a cell is the divergence of a velocity field over a cell is equal to the fluxes of that velocity field through the faces of that cell. So these partitions of unity, these generalize this idea of a cell. And what we want, though, is this idea of a boundary operator. And so let me just play a video to give you a sense before it gets mathy, right? These 2 red lines are 2 partitions that are splitting up the unit interval. And this blue line is going to be this generalized notion of a boundary, right? So as these partitions sharpen up, what we want is something that's like a direct function, right? It's like a signed function that says what the boundary of these two, what boundary is shared by these two partitions. Turns out that that thing is something called a Whitney form. And so I'm going to quickly, I don't get too bogged down in this math stuff. But I'm going to quickly introduce what a Whitney form is. So the idea is you take barycentric coordinates. So you take the vertices of a mesh. Barycentric coordinates are a way of doing interpolation on a tetrahedra that reproduces constant fields as well as first order polynomial fields, right? And this constant reproducing property of this interpolant is a partition of unity property. So you can see that these barycentric coordinates are actually chopping up a cell in a certain way. You can view them as that they're attributing different parts of the volume of the cell to different ones, to each one of these vertices. And so the idea with Whitney forms, they're presented as this like abstract thing, but it's actually really concrete if you get past the mathy details. So the idea is you start with this barycentric interpolant, and then you apply this formula in order to arrive at higher order polynomials, right? And you get it just by evaluating this formula in terms of vector calculus. It reduces to this really simple thing. And whereas the barycentric interpolant approximates nodal values, the higher order ones approximate tangential. You have degrees of freedom that look like the tangential component along the edges of a face. The next higher up ones describe like fluxes through faces and so on. And so by doing this, that has these remarkable properties that you naturally get all of your conservation structure by building your finite element space in a way like this. You exactly get conservation statements that fall out. And so that's how you can preserve all of these things discretely. Maybe I'll just leave it at that, right? I can make a bigger deal about this, but this is what you need in order to look at electromagnetism and so on. Let's skip this. How to actually build it. So by coming up with these Whitney forms, and because of the way, so the idea behind what we're doing is that we will apply that same construction, but now we'll do this to this machine learnable partition of unity instead of to barycentric coordinates. That's the idea of the construction. I'll skip the details for this cred. But the punchline is that these Whitney forms, once you found them, they induce a weighted graph, right? So what you get is a relationship between the mass matrices of these Whitney forms and the graph derivative operators that I introduced before. So once you play with those partitions, they define these graph boundary operators. And so by trying to get Whitney forms which match data, they will reveal a graph that you can work with. And these graphs have this conservation structure built in, right? So they give you something like a sum of equal and opposite fluxes for a divergence and so on. And so I can get into the construction about how we actually do this. There's different architectures, there's different strategies for how to do it, right? But the point is basically you just need a partition of unity, and it needs to be one that you can integrate. You need to perform quadrature in order to look at variational methods for PDEs and stuff like that. That's maybe less interesting. But the point is that at the end of the day, we get this equality constraint optimization problem. So very similar to the one I presented before for the pure graph setting, right? But now we're saying instead of just learning these graph operators, now we're learning the geometry, right? By learning this partition of space, we induce all of the physics that we're going to discover. And so we say, all right, give me a model which best matches like the potentials and the fluxes of some solution, and play with the partitions in such a way that it will satisfy those kind of conservation balances that I described before. And in that way, it'll latch on to, like, here's a partition of space, right? So in this case, this is just a nice simple diffusion problem, but you have a discontinuous diffusion coefficient, right? So these are like strips of different conductivity, and you have a solution where you apply a different unit flux across the whole thing, parallel to those strips. And the partitions that we do, that it identifies, is it latches onto these things. And now it learns, we don't tell it it's a diffusion process. It could be advection, it could be whatever else. But if it identifies the flux balances on these guys, and can reproduce stuff like that. So, so it's a toy problem, but that's exactly how we use this to build a digital twin for batteries, right? So these are like huge calculations that they do at Sandia. They take a CT scan of an as-built lithium-ion battery cathode. They have these huge automatic TEP meshers, which will build a TEP mesh from that CT scan, billions of element simulations, and now they can actually simulate the percolation pathways through the material for a lithium-ion battery. And the way lithium-ion batteries fail is, as you load it and unload it, lithium aggregates and causes it to swell. When it swells, you get a fracture that occurs, and it's like a crash on a highway, like it shuts it down. And so the actual transport would get rerouted in that case. So the challenge with actually modeling this is you need to actually design something at a continuum scale, but it's failures driven by this kind of mesoscale process. So what we do is, we do a handful of these simulations. We have like 10 simulations or something like that of a given battery. We run it through this control volume analysis. It's identifying these pathways and fitting a model to it. In this case, 10 elements, right? And so now we can solve this 10 element model, and it reproduces a true solution to something like 0.1% error. But simulating the system, it's inverting an 8x8 matrix, not a 6 million matrix. But we're preserving the conservation structure, right? So it gives the correct like mass flux in and out of this thing. We do the same thing for semiconductors, right? You can look at the nonlinear diffusion equations. In this case, you could go to TCAD, you could actually solve this thing. And what's remarkable is like this can extrapolate. So that this is a IV curve down here. Sorry, my axes aren't labeled. From a single simulation, from a single TCAD simulation, you can get something which will extrapolate pretty well, right? And so what this means is that we can use this to, so you want to look at radiation effects and how that gives you a perturbation of nominal behavior if you have experimental data or so on. Right? All sorts of things you can do here in terms of data assimilation now for individual semiconductor components. So the last 10 minutes, so that's this framework, this one way of using graphs, which is really just to build the data-driven forward simulators in the system scale digital twin kind of setting. Hopefully it's clear how that can map on, like we've looked at similar things for like laser diodes for silicon photonics. There's other areas where hopefully it's clear how that could actually map on to like neuromorphic codesign, which I guess is the focus of COINFLIPS. But next I'm going to show a different way that you can use graphs, which is really related to this causality stuff that I mentioned at the beginning of the talk, right? And once you can identify and exploit causal mechanisms, now you can use that as a way to perform AI-driven scientific discovery. So one project I'm not really going to talk about, that I'm part of at Sandia, is this Beyond Fingerprinting Grand Challenge LDRD. And the 10 million yard view of it is that we have a bunch of kind of high throughput experimental data where we're exploring a very high dimensional design space to look at new materials under different fabrication conditions, and then test them, but in a way where we can explore like tens of thousands of different fabrication conditions over the course of a day, which is something like completely, it's very new to attempt something at that scale. Usually people just do like 10 experiments or something, material science. And the idea, the part of the project that I lead is, can we design AI algorithms that will ingest all of this data? It's multimodal data coming from different kinds of material characterization and so on, and use those to steer this process in kind of like an optimal control and so on. And so we look at 3 different systems. I won't talk about the specifics of them, but all of these have a ton of parameters that govern the performance of the system. And they all generate thin films whose strength or electrical conductivity or whatever, some properties we would like to optimize. So the idea about how we do this, and this is the point I did want to get to, is that we put together this machine learning architecture. It's basically variational inference. It's like a variational autoencoder, where you combine all these different multimodal, these different modalities that encode the performance or the microstructure or so on of these different materials, fuses them and combines them into a given latent space, and then imposes a Gaussian mixture prior, where each component of that Gaussian mixture we would identify as having correlation across the different modalities, right? So in this one example, I'll play the video again. This one example, we have 2 different 3D printed lattices, for example, as well as stress strain curves for each one of them. And so those are 2 different modalities, and you can see in the latent space, it's trying to fit a Gaussian mixture model to them, swapping points back and forth between these 2 red dots, or the centers of these 2 clusters. Once it has sort of disentangled this data set, it's found 2 different geometries for the 3D printed lattice. It's called an octet and a gyroid. It doesn't really matter. As well as fit a physics model to the 2 of them where the mechanical response is different. So the way to think about this is that we can take these surrogates that I discussed in the first half of the talk, right? And we can use them to disentangle from experimental data like X-rays or all these kind of modalities that it's not useful to do physics-based modeling for, right? They just give you some spectrum or some microscopy or so on, but they're just an image, right? How do you tie that to the physics? But now we tie it to the physics by identifying clusters in a latent space where they do share some correlation. So this, so here you can see you get 2 different mechanical responses. This is what it looks like for the 2 of them. And there's lots of interesting details here. Like you can do UQ with this and so on. A couple more examples. We tie this to models of heat transfer into like the melt pool of a laser powder bed fusion setup. For an electroplating setup, we have a surrogate for the electrochemistry, right? How is gold being deposited to make a thin film on top of a substrate, and so on. So I'm going to come back to the initial stuff that I was talking about, right? Like if we have this digital twin, really what we would like to do is identify causal fingerprints, right? We want to find not just these relationships. What I just showed is, kind of just correlation across modalities, but what we want is causation, right? Like when you have in the Earth model and the land model of E3SM, if it predicts a wildfire, that will predict, that's the precursor to a monsoon or a hurricane in the atmosphere model. And we would like to be able to identify that and dispatch emergency services, for example, right? So the idea is we'd like to perform the kind of stuff I just described, but now use a causal graph in order to do it. And so the idea is now, instead of fitting a Gaussian mixture to the latent space, we're going to, and recall a Gaussian mixture is a Gaussian distribution conditioned on a categorical distribution, right? So the nodes of those clusters, right, that's this categorical distribution. Instead, we're going to discover a DAG, but where the nodes of the DAG correspond to these clusters, right? So now instead we'll have Gaussians conditioned on what node of the DAG you belong to. And so the challenge with this is, in order to train something like this, it needs to be fully differentiable, to throw gradient descent at it and do all this kind of stuff. So you can use this graph exterior calculus to parameterize a DAG. So the idea is we're going to have a learnable score function, these size, and we're going to take the graph gradient of that. And now, because the curl of a gradient is equal to 0, you can use that to prove that this can have no cycles. So if you define an edge as this kind of, you view this as a temperature modulation of this kind of smoothed direction field, right? The gradients that say where it flows going on in the graph. You can use this to sharpen it up And this gives you an indicator function that says, are the fluxes induced by these scores positive or negative? If it's positive, then you have an edge going in one direction. If it's negative, it's going the other direction. But this is guaranteed to not give you cycles, right? So that's kind of the idea. I know this, it's a totally different application than this exterior calculus stuff. But now you get a version of gradient, you get a directed acyclic graph that you can throw gradient descent at, and now we can embed it in the latent space of a variational autoencoder. It's probably way too fast to actually get the details, right? But hopefully for like a one-slide version of it, that gives you a sense. So here's a concrete example. So we have this data set that we put together. And so we have a bunch of circles with different radii in different positions. But there's a generative process that we used in order to build this data set, right? So the way we put it together is we randomly selected a color, but then we chose the size of the particles conditioned on what color they are, right? Like red circles are going to be big, green circles are going to be small, for example. And then we have a shift of the circles, right? How far to the left or to the right. And that will be a function of both the color and the size, right? And so what's interesting about this is, of course, you can throw any sort of machine learning at this and you can reproduce picture, like images, same way you learn cats and dogs and so on. But what's interesting is that we've set these conditional distributions so that they're ambiguous, right? So if you only see the images, you could not tell what the color would be, right? So that meaning that the Gaussian distribution for the shift of a red particle overlies the one with the red particle, right? So just from seeing the shift, you couldn't infer the color. So in that case, there's some ambiguity there. And what we would like to do is infer what the actual generative process was, right? And then get our hands on. So hopefully that makes sense. It's all this causal stuff. It's like torturous to talk through. But anyway, so that's the point. So now we throw just a pile of images at this VAE type architecture, and it identifies a DAG. And in the latent space, we get these clusters, but each one of these clusters correspond to the different kind of permutations that you could get, like red, green, big, small, left, right, and so on. And it disentangles that. And now we've learned the generative process, right? So that's what we're hoping. That this mimic center it's a new center. It's in the we're in the first year of a 5-year project, but this is the architecture that we're building up in order to apply this to more scientific settings. So hopefully that kind of gives a taste of where that's going. One of the postdocs who's involved in the project, Jonas Actor, is involved in this this aging and lifetimes project, where basically you have gallium nitride transistors that you flip off like 100,000, like off and on 100,000 times. So this is a way to simulate aging, and it has some important implications at Sandia. So the idea here is that we can combine all these different kinds of modalities, like direct numerical simulation, TCAD, the actual experimental device where we can just measure it, look at a voltmeter and current reader, right? And we can generate these time series profiles of all these switching, and so on, right? We can feed all these things in, but we can look at, in these different modalities, what precursors do we have here? So maybe I want to make sure I leave a little bit of time for questions. I wanted to talk a little bit about, for neuromorphic computing, in my mind, the real direction that you can go with these graph neural networks is something that looks a lot more like the brain, right? So when you look at a current spiking neural network, those are really built around like a single neuron level, like leaking a grate and fire type description of the physics. But when you look at the brain, it's actually hierarchical and it's unstructured, and there's sparse connections between different things. So the real, I would advocate that the graphs are the natural place to do this. And part of our centers, we're building these spiking neural networks on graphs with that in mind. But there's a real challenge in terms of co-design because graphs are the hardest thing to get into hardware. There's so much sparsity and irregular computation and so on that you can't really design for it. And in the same way that the exascale computing project, right? Like when they want something that hits the exascale, they're not doing super unstructured computation, right? Those are very structured grids that they look at. There's very like nice problems with exploitable structure, so that way you can get it into hardware in a smart way. So there's this really interesting push and pull for neuromorphic computing, right? Where graphs are the obvious natural architecture that you should be going after, but they're also the hardest to get into hardware. So, maybe I'll just close with that as food for thought. It's interesting to think about how you can meet in the middle, and how do you map these kind of more mathematical machine learning architectures into hardware, even though it kind of resists it. So stop there and take questions if there are any.